Okay, hello everyone. The webinar is now starting. I'll maybe allow one more minute for a few extra people to come. See a number of people have already joined. Maybe I'll give it another 30 seconds and then I will start talking. Okay, I think we can now start. Give enough time for a few more people to join. Welcome everyone. Very grateful that you're all joining us today. And so what we're going to be talking about today is the concept of design for testing in photonics. And this is key to standardizing the testing process for PICs in general. And what this means in essence is designers factoring in test requirements and restrictions from the very beginning of their PIC design process. This can be challenging in practice. This means aligning the requirements of foundries with those of testing partners, and there are pitfalls in this. But our speakers today are going to show us how we can address those challenges. So from the Luceda Photonics side, we have one of our speakers, my colleague Aysan Anamoradi, who holds an MSc in Photonics from Ghent University and has been an application engineer at Luceda for around a year and a half. And her role at Luceda is supporting our customers with designing their PICs, and she also helps deliver online and on-site trainings and webinars. And also with us today is Minguillon from VLC. He's an application engineer, and he plays a pivotal role in supporting the clients throughout the design and testing phases of PIC design. He holds a master's degree in material science from Utrecht University, and he's responsible for developing, maintaining, and expanding the customer relationships and ensuring their needs are met with tailored and innovative solutions. Just one more thing from the two companies. So Luceda today will focus more on the design enablement process and seeing how a streamlined design test workflow can be implemented and then realizing this testability from the start. And then VLC will present their outsourced photonic design and test services and explain the importance of layout rules for successful testing. A little overview of the schedule. So after this very brief introduction, I will hand the floor over to my colleague Aysan, who will speak from the Luceda side for the next 10 to 15 minutes. And then we will hand the floor over to Miquel to share the view from the VLC Photonics side. And then we'll save the last 10, 15 minutes for questions. Regarding questions, feel free to post questions in the chat any time, and we will pick those up at the end. But of course, at the end of the session, you'll have time to unmute your microphones and ask us questions that way. So without further ado, I will now hand you over to my colleague, Aysan, who will talk about Luceda Photonics.
Thanks, Craig, for the introduction. And hello, everyone. I'm going to share my screen. Okay. Hello again. My name is Aysan again, and I'm application engineer at Luceda Photonics. Today, I will walk you through how Luceda supports design for test using our test design kits or TDKs, and how this not only improves testing, but actually makes the design process smoother and more efficient. So first, I will give a short introduction to Luceda. Luceda Photonics was founded in 2014 out of the Belgian photonics ecosystem. It was created with the long-term goal of enabling photonic IC designers to enjoy the first-time right experience as electronic IC designers. Our mission is to accelerate the time to market of PIC design teams by helping them set up a flexible and efficient design flow. We have presence around the world, including a branch office in Shanghai. We have a partnership with Spark Photonics in North America, and also we have resellers in Taiwan and Tokyo. By using Luceda, you will have access to a team of photonics experts who can help you achieve your goals. This slide shows an overview of the Luceda Photonics design platform. It consists of our core product, PICs, which includes features such as a circuit and component design, optical and electrical routing, and etc. You can simulate components using our built-in EME solver and simulate the response of circuits both in frequency and time domain. You can also visualize the schematic of your circuit using Canvas and perform post-layout validation. Finally, you can export your design to a GTS format. We also offer specialized modules such as AWG Designer, which helps you design AWG from a specification list, and also IP Manager to help you manage your photonics design IP. Also, we have offer integration with third-party softwares like ANSYS Numerical, CSD, and also TiD3D. We also have a link with Checkmate BRC, link with Siemens EDA, and also we have link with System for system-level simulations. At the left, there are available design kits on Luceda platform. We have a variety of PDKs on different material platforms. There are also design kits for assembly and testing, and these designs support integration of testing and assembly in the design stage. Today, I will demonstrate how Luceda enables the integration of testing into the design flow. So let's start by this question that why design for testing matters. So testing is often thought about too late in the photonic IC design, but leaving it until the end can lead to some serious issues. For example, the designs that are hard or even impossible to characterize. And this will lead to delays, extra fabrication cycles, and unnecessary costs. So here, for example, without design for test, a chip is designed, it is fabricated, but testing can fail due to several reasons. And so the designer have to redesign the chip. It should be refabricated so it can be successfully tested. But with design for test, the testing preparations are done in the design stage, and they are integrated in the design flow. So once it is fabricated, it can be successfully tested. So it is very important to integrate the test requirements in the design flow. Here, for example, is a design without considering tests. It can be very difficult to align due to the presence of couplers all around the chip, everywhere around the chip, and also even some ports may be inaccessible because of the dense placement of these ports here. There are also common missing or misplaced testing structures, and chip size can be incompatible with testing equipment. It can be too small or too large. And also, even if it is testable, it requires manual setup for each chip. And it increases the chance for mistakes and slows down the entire process. Here we see design that follows the test requirements. We see that the placement of the electrical and optical IOs follow the convention of testing. For example, here are the ports for inputs and optical inputs here, optical outputs. These are the pads, and also if the chip requires RF connections, these RF pads can be placed at the south of the chip. So once the designer decides to integrate the testing requirements in the design stage and the first steps, they can do it, of course, manually. They have to ask the test house about chip layout restrictions, such as size, IO pitch, placement, and other testing recommendations. And once they have this information, they have to calculate the positions of each port and manually generate and place them. They have to manually draw and place fiducials and create custom test structures. But it can be too much work at the design stage, and it requires a lot of time and coordination, and it is between the test house and also the foundry, and it is always very easy to miss something. So Luceda enables this flow by test design kits or TDKs. Luceda platform focuses on first time right design, and instead of leaving testing as an afterthought, we make it a part of the design flow by providing TDKs or test design kits. And these TDKs include layout rules, test structures, and best practices recommended from the test partners. And these are packaged in a way that makes it easy to follow. And it reflects what test houses need and turns them into something you can directly apply in your design. So in the Luceda platform, you can embed TDKs directly into your layout environment together with the process design kits. And these TDKs are not just theoretical guidelines, they are practical tools. You will work with automated checks that can guide you toward a testable design. And by this, you can offer a first-time right design. You will have fewer surprises post-fabrication and also smoother test cycles, and finally faster time to validated results. Here is a comparison between a manual design for test and using Luceda TDK in the design flow. So whenever layout constraint violates a testing requirements, for example, a chip size is not compatible, the designer can see an error or warning without going through the design manual themselves. And so the placement of the ports are also automated. The pitches, they are generated also automatically and placed automatically. And the predefined fiducials can be chosen in different shapes, and they are placed also automatically. Also, some tested waveguides are generated when by using Luceda TDK. Here also, again, some parameters in the TDK that the designer can change or specify. So starting from the template, they can specify the size of the template they want to use according to their PIC size or chip size. And then they can select the coupler from the PDK and also specify the number, the pitch if they want. Otherwise, it will default to some recommended values from the test house, and they will be automatically placed. The same for the pads. They can be it should be just selected from the PDK. Again, for the fiducials, they can have control over the shape and as well as the location of them. So now let's see how we can integrate this TDK inside the design. So first of all, we need to import a PDK, and then here VLC TDK is imported afterwards. And now we can instantiate or make a frame of the testing design kit. For example, based on my circuits, I would require, for example, this template vertical single fibers RF pads, which makes this frame. And also then I can specify the PDK, the coupler from the PDK, the numbers, and other layout information for the placement, also for the bond pad. And then for the fiducial, I selected circle shape that should be placed in all corners of the chip. So now if I use this frame with these numbers, I see that some warnings or errors that says, for example, the optical port pitch are not standard and are not recommended by the design test house. So now I can change it And then for the bond pad size, for example, I give a 85 micrometer dimension, but I can see it is not compatible with the restriction from the that is coming from the test house, which says it should be between above 90. And also I can see the recommendations as well. So although 90 is acceptable, but the test house recommends another value, so I can change the dimensions of my pad without issue. So once this frame is placed and created, I can now import my design. For example, this is an optical phased array without any connections to ports, also some MZIs with arm length difference, and also some spirals. I can place them in this frame. I can place them individually or relative to different parts of the circuit or relative to each other. It's my choice. And then after placement, now I can make connections. For example, this is an example connection which connects the coupler put here in the frame to the port of the OPA. And I can use different connectors for bundle connection in optical domain. I can use a Connect Manhattan bundle to connect a group of ports at one side of the chip to the ports to the other part of a chip. And then I can use a connect electrical for individual electrical connection or bundle connection for electrical connections in a bundle. Then I can also see different layers from the foundry in the IPIS visualizer, as well as the layers that are associated with the test design kits. Now I can, once I see the layout, then I can export it to GDS and send it to the foundry, but I can also exclude the layers from the test design kits that are unknown to the foundry. So this is the final chip. And now everybody is happy because the designer, the foundry, and also the test partner are happy because the Luceda enables a smooth collaboration between different partners. And this reduces back and forth coordinations and misunderstandings, and also saves a lot of time and cost for everybody. Thank you. Stop sharing.
Okay, thank you, Aysan. So now we will pass the floor over to Miquel from VLC to talk about testing from the testing service perspective.
Okay, so thanks a lot, Luceda, for having me. I will present now. Let me know if you can see the screen.
Yes, we can see your screen.
Now full screen, right?
Yes, full screen is good.
Okay, so, well, Craig already introduced me. I'm Miquel from VLC, application engineer. And today I'm going to talk about design for testing in photonics. And also I want to give an overview on challenges that you may face during the testing. So let me start by introducing VLC Photonics. We are a service provider around PIC development. We focused on design and test, and we are application and material agnostics. This means that we support customers throughout the entire development chain, no matter application or material. We were founded in 2011, so we are a pretty well-established company, and we have all the facilities in Valencia. We were a spin-off of the university campus, and now we are around summertime, we will be moving to a new facility. In 2020, we were acquired by the Hitachi High-Tech Group under the Value Chain Division. So nowadays we are 40 employees, most of them engineers, 75%. So a pretty highly technical company, and 33rd of them are PhDs. So Hitachi is a really big company, but our division, which is the optical component supply chain, what they do is that they act as a trading business for optical components, Japanese optical components, and they sell them overseas and vice versa. So they were trading between overseas optical components to the Japanese market. This was mainly for the transceiver market, and Hitachi thought that this market was going to suffer a transition into integration, and they wanted someone that has the expertise and the knowledge on this technology to support them, first understand it well, and also develop products around this technology. So because we are involved in the entire development of a PIC, we have a great overview on what it takes to create a product. So we define it as a cycle, and this is because to create a product, you need several iterations of those. You will start with a photonic architecture where you specify components specifications, circuit level specifications, and you end up with a system architecture that then you will design based on that. And for that, you can model or simulate your components or use the ones in the PDK. And then you will create the layout. That this layout will be transferred to the foundry with a GDS file that then they will create the mask and fabricate your devices. Then the foundry will provide either wafers or dies, depending on the fabrication run that you did. And then you have to characterize those electro-optically. This is because the foundry doesn't do characterization of those devices. It just does a PCM controlling kind of test if the fabrication has done correctly. And then you need to test because the packaging is a crucial and expensive step. So you want to know which are the working devices before you package. Also, in time perspective, how you create a product is with these phases. So you will start with a product development that transitions or goes from an idea to a prototype that, for example, if you want to pitch to investors, it's worth to have prototype than to show something. And then you go through the pre-series and pilot series to build the statistics and data to optimize both the component performance as well as the fabrication process. Once you have everything set, you can ramp up once the volumes come and then move into series production to fit your market need. In VLC, we support from product development to pilot series. And then we have a route to transfer, for example, the testing or the packaging through the help of Hitachi. So we can transfer the process to an OSAT that they will do the rest of the process. So how does this TDKs that we are talking today about integrate into the design flow? So this is kind of the cycle or the flow that you will follow for designing a PIC. You will start with photonic component design, where you define and design your epitaxy, doping conditions, simulate your components. Or if not, you can use the ones from the PDK that are freely available in the foundry that you are going to fabricate. And then with those components already set, you can start doing the photonic circuit simulation. This is basically running virtual experiments to tune and understand the fabrication tolerances. And then you will lay out your circuit based on first the design rules from the foundry, and because this has to be DRC checked. And finally, you give the GDS file to your foundry. So in VLC, we highly praise on thinking when designing about the testing. And this means, for example, thinking about which equipment and instrumentation you are going to use. Then you can plan accordingly based on the bill of materials, identifying and setting the electrical and port location, as well as the pitching between the electrical parts or the optical ports. And also, for example, setting the measurement system analysis, which is basically the validation that your setup, your testing setup is done correctly, which test do you want to do in this campaign, to then finally run the automated testing. For this, in VLC, we developed a PDF file that we were sharing with customers that is basically a set of rules provided by us. So your chips are testable in a standard testing setup, like a wafer level tester or a die level tester. With the help of Luceda, we have implemented this TDK PDF file into a software tool. So now you can go to the Luceda software, as Aysan explained, and use our TDKs to make them compatible to a testing setup.
Okay, and Miguel, one more thing before you go to the next slide. At the bottom of your screen, there's a zoom bar, which is obstructing a part of the bottom of your slide. Yeah, yeah, that's it. Okay.
Yeah, sorry.
No, no worries.
So now that we understand how we integrate these TDKs into the design flow, I want to explain several issues that we found in customer projects that first conclude in a non-testable device, or maybe it affects the cost of the testing campaign. So let's just start with this die configuration. In VLC or in the standard setups, normally the west and east sides are optical ports and the north and south sides are electrical pads. This is because in the standard wafer level setup, the optical ports probers are located in these east and west sides, and the electrical probes are located in the north and south. For the optical ports, you can also put electrical ports there, but for the electrical ports, you cannot switch it to optical. So how do we tackle with this problem, right? So if we have a wafer that all the chips are placed in the same direction, we can flip the wafer and then it becomes testable. But if your chips are some of them placed in this direction and some of them in that one, then you need two setups to test those. You need one configuration to test those chips, and then you will flip the wafer to test the other ones. This will mean that you will require two different setups for the testing campaign, which is basically two NRE costs, which can be up to 10,000 euros. The second issue that we see is when the customers, instead of putting the optical sides next to each other on the opposite directions, they put it perpendicular. As mentioned before, you cannot put in the electrical ports an optical one. So this becomes non-testable. Following this, what we have is the electrical pitch distance. We find that sometimes the customers don't understand the importance of electrical pitch, and they design based on the requirements or the space that they have in the cell. And you can, for example, design a 60 micrometer pitch on the electrical side, and this is not standardized. So you will need to buy a custom probe that can be up to 100 euros for that. The solution, just use regular electrical PICs like 100 micrometers, and then you can use a standard electrical probe. There's another issue that we faced during analyzing the projects, that is not all the electrical pads have the same pitch. So this means that if you are using a regular electrical probe, you will not contact all the electrical pads. With this, you can buy a customized probe, but you have to consider something important. That is, if imagine that in this distance you have a test structure and you have a needle contact in this test structure, you can damage this structure, and then this will affect your testing campaign. So at the end, what you are doing here is increasing the price of the probes by around 500 euros. Then there's the other problem, that is when you have the optical ports really close to the electrical pads. This can cause for example, if you are using grating couplers, the fiber array to invade the electrical pads, and then if you want to come with an electrical probe, this will collide between each other. This can be solved by purchasing a leadless probe, but sometimes, even though you are purchasing a leadless probe, then you cannot test. So take in consideration the distance between the optical and electrical pads, or the optical and optical. Also, when you are, for example, some customers, what they did is they put two rows of electrical pads into the same chip that has to be contacted all together. In this case, you can use, for example, an custom electrical probe that can contact both rows at the same time. Another solution could be that you enter from this side with an electrical probe and from this side with another electrical probe. But what could happen is that you collide with the optical ports. So these solutions you will incur with around 500 euros of extra cost due to this customization in probes. Finally, and based now moving to the assembly or packaging part, if your distance between the electrical pads and the edge of your chip is really high, for example, 5 millimeters, what happens is that you cannot do the wire bonding if you need to do it into a PCB or something, because there is some length constraints in these wire bonds. Otherwise, they will fall into the chip. So now that we see some of the problems that we face during customer projects, and we have to analyze and customize the testing that at the end the customer incurring extra cost, I want to give an overview on why it's important to do this photonic testing. Photonic testing is really important because, first of all, it helps you define and refine your fab processes to optimize it, for example, to increase the foundry yield. This will also allow you to evaluate this yield and contrast it with the one given by the foundry. You can also optimize the functionality of your components and your circuit by iterating into the cycle, as well as sorting the known good dies or wafers for example, after packaging. So what are the challenges that we see when someone wants to internalize this testing? We see three main challenges during this testing, which are volumes, high speed, and reliability. The first one, we define three phases of volume. The first one is R&D and prototyping, which can go from 1 to 10 chips. It can be done in an optical setup, etc. Then the engineering and pilot production, which goes from 10 to even thousands of wafers, which is more than one fabrication lot. And then the high volumes, which goes from 1,000, 10,000 wafers per monthly flow. These high volumes are done by the OSATs in Asia. It's a pretty well-established market. It's done in electronics, so no problems about that. The R&D and prototyping can be done at a research center, for example, in an optical setup. But then once you move into engineering and pilot production, there are some things that you need to consider. First of all, you need to have a clean room facilities that allows you not only to test your actual needs, but also to scale once the volumes arrives into your products. Everything has to be ESD protected to avoid electrical discharges into your chips, as well as you have to have first equipment and instrumentation redundancy to avoid any delays in the testing campaign, as well as everything has to be calibrated and everything has to be stored in a database with all the documentation and tracking of this information. At the end, once you test thousands of wafers or tens of wafers, you need to have a certain degree of automation. And to do that, you need an experienced engineering team. That we see that this has been an issue. All the companies are facing issues regarding recruitment. So this can be quite complex tasks. In VLC, we tackle this issue by having a scalable test infrastructure with over 500 square meters of glass ISO 6 clean rooms. Everything is fully ESD protected, and we can do from visual inspection, both at the chip, gel pack, or wafer, up to 300 millimeters, as well as the testing. So for testing, we can do automated die level and wafer level testing, and we allocate up to 12-inch wafers. This, at the end, generates massive experimental data and statistics, and you have to have scripts to process this data, analyze them, and then share it with, for example, the customers in our case. At the end, this has to be also transferred or thought in a way that you could transfer to an OSAT once the high volumes comes to your market. As well, in terms of the optical testing, and because we are material and application agnostic, we have to cover a wide range of wavelength ranges. So we have from visible to mid-infrared, And with that, we can do from electrical testing to vertical and edge coupling, controlling the polarization, etc. Then there's the second challenge that we see, which is the high speed on the measurements. This is regarding the lead times that it takes to do the testing campaign. So when you perform automated testing, there are two phases that you have to overcome. The first one is the MSA, which consists of installing the instrumentation and calibrating your equipment. Then you have to program the scripts to automate both the electrical probing and optical probing, as well as the data acquisition. You have to set up the storage database, and at the end you have to make also a test plan where it says what is the validation criteria that will follow. For example, you set a number of tests that you want to do, that if these tests are correct, you are validating the setup, and then you can go or transition into fully automated testing. In this phase, most of the work is done by engineers and less by the tool. But once you move into automation, and this is inversed, and most of the work is done by the tool. In the test campaign, most of it is basically probing and the measurement acquisition. There's a second variation of this high speed, which is related to the signal testing for the markets of telecom and datacom, which are the driving markets in photonic integration. This is because you need to detect the signal integrity issues early to optimize the performance of your building blocks. This optimization or early optimization of these components will reduce the time to market. And at the end, with this test that you are going to perform, you are making sure that your product is compliant with the standards of your industry. When testing or performing this testing, you need to think about how this will scale in the future. And for that, you need to start implementing or integrating your testing setups into the wafer level. This can be a complex task when talking, for example, with high-speed equipment, but is something important if you want to scale in volumes. It's the same as, for example, the equipment that you buy. You not only need to think about the transceiver or the components that you have now, but also the future needs that you will have, for example, in terms of high speed. So for this transceiver market, the main component or the most important component that we see is the modulator. These high-speed modulators can be done in different material platforms like silicon photonics or thin film lithium niobate. But at the end, what you need is to have equipment to test up to 110 GHz, which is a light wave component analyzer. At VLC, we have this equipment, then we can go up to 110 GHz in the full C and O band. And not only that, if you want to test kind of the full RF characterization of the component, you need to also validate or test the S parameters. And for that, we have a VNA that is also capable of going up to 110 GHz. Then there's also the system level testing for transceivers. This can be done at both at the chip level or a packaged transceiver module. And this test is done to ensure that your product is compliant with industry standards. There are two main tests that you have to do for this. One is the eye diagram testing that analyzes the signal quality and integrity in real time, up to 112 gigabaud for standard reasons. And then the bit error rate testing that evaluates the link reliability and error performance. For this at VLC, we have procured and we have new equipment that can test those two tests, which are real-time oscilloscopes that goes up 100 GHz bandwidth, AWGs that goes up to 256 gigasamples per second, and BERT analyzers. And finally, there's the third challenge that we see, which is reliability testing. This is something that is getting more traction. I was in OFC in March or April, and most of the people were talking about the importance to make reliable products for the commercialization of those. Reliability testing can be done at the wafer level, chip-on-carrier or package level, but something that has to be noted here is that this type of testing is pretty much application dependent. So ultimately has to be done by the end user. What we recommend at VLC is that for faster development time, we recommend it to test it at the chip-on-carrier level, because then you avoid the packaging or the high cost of the packaging, and you can iterate much faster on your design. Despite being a test that is highly dependent on the application, there are still some commonalities between markets. The first one, and in VLC we are equipped to support this kind of common testing, and we have ovens to do high low temperature. We have dual chamber to do thermal shocking, as well as burning racks for testing, for example, lasers. For high low and temperature test, basically you are doing is accelerating reactions at high temperatures and mechanical failures at low. Thermal cycling means accelerating this thermomechanical fatigue of your devices. Burning is accelerating the electric breakdown of your components, as mentioned, for example, lasers. And the moisture test is basically exposing your devices into moisture to accelerate the corrosion. The reliability testing has several challenges attached to it. The first one is you want to perform this type of testing to your devices without breaking them, because at the end it's a passed or failed criteria. So what happens is that this makes the optoelectrical probing much more complex. Also, because you are testing at the system level, kind of chip-on-carrier or package device, the root cause analysis of your failures is even more complex than, for example, when you are analyzing what it fails into a component testing. This is because you have several components interacting between each other, and at the end you are reading the output signal. So you have to analyze what is the main driving factor that makes your chip fails. This is even more complex or challenging once you move into hybrid integration, because at the end you are testing different chiplets from different materials, and you have to analyze which is the failure mechanism of those. So this is something that you need to take into account when doing reliability testing. Finally, I want to mention some basic test assemblies capabilities that we have in-house. This is because we think that, or we want to continue supporting our customers on the testing side for faster prototype validation, and its capabilities extending from wire bonding or flip chip to fiber pigtailing. As mentioned, this is capabilities meant to support on the functional testing side, but we are not packagers. This is done by our partners, and we don't want to enter this business. But we thought that to allow for faster development time for our customers, it would be good to have these capabilities in-house. So to finalize my presentation, I want to give you some takeaways or notes that I think are worth having it when thinking about testing, internalizing your testing. First of all, you don't need to do this CapEx investment on the testing equipment and the clean rooms. I have to say, for example, the high-speed equipment is really expensive. So it goes up to 1 million so per equipment. So it's maybe worth considering outsourcing this type of test. Then you count for engineering expertise from day one. You don't need to first hire new engineers to perform this test or train them, but you count on a partner that is able to do this kind of test. At the end, what this does is speeds up the response and the time to market of your product, because you just keep hiring and training, reducing the procurement time of your components. And at the end, VLC, for example, has already a supply chain agreement that you are entering once you contact us. At the end, you de-risk product development. because we are experts on this field, and we have faced many different challenges across our history. And for that, we know how to solve issues. So using this agile methodology that we implemented in-house, we can support and have daily interactions with the customers that de-risk the product development. So this is it for my presentation. I hope you like it. And if you have any questions, I will be happy to answer those.
Hello, sorry, my mic my mic was still muted. Yeah, thank you, Miguel, for the nice presentation. So we can now open up the floor to questions. If you have questions, please feel free to unmute your microphone and ask away.
Hello.
Hello?
Hi, can you hear me? Okay.
Yes, we can hear you fine. Yes, please ask
Oh,
away.
perfect. Thank you so much for your presentations. So just a bit of background, I'm a PhD student working on PIC design, and this is my first time coming across the concept of a TDK instead of just PDK is what I've been familiar with. And I've been using Luceda as well for doing some PIC design in the past. So I was just wondering, are the TDKs specific to a foundry's own PDK, or is this kind of like a general like document that you can use for, I don't know, just in general PIC design, and how do you access it?
Yeah, so these TDKs are generic, so it can be applied to every foundry. At the end, what those are is a template, and it's parametric. So you decide kind of the size of your reticle, and you adapt it to your needs or the foundry that you are testing.
Also, maybe I can add that in the Luceda platform, you can import the PDK, and then you can also the TDK together with the PDK to select the couplers. So they are not conflicting each other. Each you can get some warnings for the, or like guidance for the layout design, but yes, you can, and also they are, for example, VLC TDK can be used with other PDKs, with any PDKs that are also in the Luceda platform.
And it's included with the Luceda license?
Yes, once the PDKs that are PDKs and all design kits, TDKs and ADKs, you don't need to pay for them. For some of them, you need to just have an NDA signed with the like design kit foundry, but they are included in license.
Okay, perfect. Thank you both.
Yeah, you're welcome.
Yeah, there was one question in the chat from Ahmed from OptiWave. Maybe you can ask it.
Sure.
First.
Thanks. It's a great presentation. And question is about you mentioned that you outsource the testing capability of these chips. Just asking how much is the cost would be, let's say, per chip, or to do the like VNA testing and lightweight testing.
Yeah, so this depends on case by case. Also,
just rough numbers.
I have to look at the layout of your chip, or we can talk if you want. We can set up a call and we can discuss more in depth into the project maybe.
Okay.
I would say that a typical, for example, wafer level testing campaign is no less than 15K, because you have this Henry that program the scripts and the probing, etc. So this is the Henry cost, but once you test more wafers, then the price per wafer is reduced, because if you test one wafer, most of the cost comes from the NRE, which is non-reciprocal engineering, recurrent engineering. But once you test more wafers, this price per wafer is reduced. And this happens the same with automated die level tester. If this testing is done manual, it's the cost is per chip, right? But once you automate it, the more you test, the cheaper it gets as die perspective.
Perfect, thanks.
You're welcome, thanks.
Okay, are there any other questions at this stage?
Hello, can you hear me?
Yes, please.
Hello. So just a background for myself, I work in a company called Quant, and we also produce chips, and I work with the layout and also the characterization. So you also mentioned that you do create a lot of statistics for all your components, for the circuits and things. So for me, the question is, maybe it's basic, but what would you say is the best way to or the best device for measurement of waveguide losses? Would you go for like the best structure for this testing purposes?
Waveguide losses, you mean propagation losses?
Yes, propagation losses. Like, what would you say is the best? How do you get the most statistical valid data?
I have to say here that I'm not a designer or an expert in the field, so probably my engineers could answer better. But I would say kind of a spiral, you will have some results on propagation. So depending on the length of this spiral, you can extrapolate the propagation losses of the structure. But this can be answered much better by my designers.
Okay, yeah. Okay, thank you.
Okay, thank you for your question. Any other questions? If not, maybe in the meantime, I have a question for you, Miquel. In terms of the die level testing, so what volumes can you support for that?
Yeah, so in terms of die level testing, now we have procured a automated die level tester that actually we are going to exhibit it in the Laser World of Photonics in June, together with Ficontech. So if you are going to the Laser World of Photonics, please stand by and we showcase the demo. In terms of volumes, what we can support is hundreds of dies or even thousands, because this is basically a gantry system that picks the dies, places it into the chuck, and then it does the full electro-optical probing automated. And yeah, we can support in a monthly flow. It depends on the customer needs, but I would say on the order of thousands per month.
Okay, good. Any other questions from the participants at this stage?
Hey, can you hear me?
Yeah.
Great.
Yep.
Yeah, and that's Miquel from Keystone Photonics. I had a question when it comes to electro-optical testing. So you mentioned some basic restrictions of how you orient the ports. I was curious about whether there are any other restrictions apart from having these kind of no-go zones near the corners and so on. So are there challenges specific to testing electro and optical at the same time?
So there are there are other limitations. For example, once you move in, so if you want to test wafers at the edge coupling using edge coupling, we can do it, but we ask our customers, for example, to dig some trenches. These trenches has size constraints. So, for example, the trench can be in the width and length sides can be 100 micrometers minimum, and in the depth side it can be 50 micrometers minimum also. And then what we ask is that apart from this, building these trenches, basically we are inserting some periscopes. So this is kind of the, you have to have these trench size dimensions constraints to do this type of testing. You also, for example, if you are testing grating couplers, you need to, we also have some, for standardized testing, we have some angle ranges that if you are, your gratings are optimized for other angles, then we will need to do some customization on the optical probe to allocate this different angle of incidence. So there are other requirements, and you can have them all in this TDK from Luceda. I just, in my presentation, I just wanted to highlight some of the errors that we, our customers had, and how this affected kind of the overall testing campaign.
Yeah, sure. Thank you. Is there a specific reason why you specifically highlighted now edge coupling for electro-optical? Do you see this more often when it's electro-optical devices, or?
Yeah, so I mean, in terms of edge coupling, we are seeing more often customers doing this edge coupling in the wafer scale, but because at the end, I think how it goes is we kind of promote this capability, and then customers are aware that this edge coupling can be done at the wafer scale, and then they don't see an issue anymore. So if their structures are optimized for edge coupling, then they start using the edge couplers. So yes, I see interest on edge coupling at the wafer scale, for example.
Gotcha, perfect. Thank you.
Thank you for your question. There was a question in the chat from Dima from PICs, and his mic's not working, but he's asking Luceda about future plans regarding TDKs and the development of TDKs. What I'd say to that is we're always looking to work with people in this space who do this type of testing. We believe in the importance of this type of standardization to help move the industry forward. If you actually would like to discuss it further, we can always set up a call after the webinar. We're happy to discuss any of these things in more detail with you. And for anybody else in the call, if you want to learn more, we'd be happy to chat about this and anything around TDKs from a software perspective. So that is how I would address that question. One other thing that was mentioned was Laser World in Photonics. Just to mention, we will actually be there at Laser World Photonics. We will have a booth. So we will have a few of our engineers and our CCO and CEO will be present as well. And we'll also be present at ECIO in Cardiff next week from the 10th and 12th of June. So if any of you are attending these events, we'd be happy to talk with you. And regarding trainings and webinars and events of this type, please check out our website. We have a list of the events that are upcoming, as well as other training events. And please check out the QR codes that you can hopefully see on the screen for both ourselves, but also for VLC. And I'm sure you can reach out to them whenever you have questions. And they will happily accommodate you.
Yes, please. Any needs that you may have on your product developments, just contact us at sales or even my LinkedIn profile in Miquel Minguillon, and we will be happy to support and discuss what are your needs, right? So yeah, feel free.
Perfect. Okay, so we're now at time. So I will say thank you, everyone, for joining the session. And thank you to our speakers today for the great presentations, very informative, and it was a real pleasure. And so thank you, everyone.
Thanks a lot, Luceda, for having me. And yeah, see you next time.
Yeah, see you next time. Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.